Good morning. I'm Greg Titus. I'm a principal engineer at Cray Incorporated. I'm here to talk about Chapel. This is something of a family homecoming for me. I thank you for the invitation. My father graduated from UI Urbana in 1954 with a master's degree in hydrology. And he's asked me to report on the condition of the campus. Yep. So let's see, page down. Uh-oh. Here we go. Here's the outline of what I'll talk about today. Give you a little bit of introductory material about Chapel, show you how compilation proceeds, talk about modules, and then the runtime. That'll be the runtime, and the example thereof will be the bulk of the talk, and then just a brief amount of future work. So what is Chapel? It's an emerging parallel programming language. Has not fully emerged yet. Design and development is led by Cray. We've got collaborators throughout industry, the national laboratories, academia. Like X10, this came out of the DARPA High Productivity Computing Systems program. So the overall goal was to improve programmer productivity, make parallel computation parallel software easier to write, to match or beat the performance of the current programming models at the time. Yeah, we're not there yet. X10 is doing a little bit better in that regard. To make high-performance software more portable than it had been in the past. So it's a work in progress. We've just released version 1.7. We do releases typically in October and April, so we've had one just go out. And there's the website for you. So the implementation, it's open source. It's all open source. Actually, there are a couple of caveats there. I'll talk about that later. But it's nearly all open source. It's under a BSD license. Target architectures are obviously the Cray systems, multi-core desktops and laptops, commodity clusters, other people's systems. And we're working toward more heterogeneous sorts of architectures like CPUs plus accelerators. Many core stuff, that sort of thing. So, how does a Chapel program work? Well, I want to talk to you in these next two slides about locality and then about parallelism. So first, with regard to locality, a program in Chapel launches on a collection of locales, what we call locales. In Chapel, that's a place where there's memory and processors. Typically, so far, that refers to a system node. The user main program starts on locale 0, as one might surmise. The other locales wait for work, which will be delivered by active messages. And locality of execution is controlled mostly explicitly, but in some cases implicitly by user code. So here's an example. You say, for example, on an expression, do some statement. What that says is move the location of execution to this locale for the duration of this statement. That locale expr need not be something explicit. It doesn't have to be like locale 3. That could be just a variable name, in which case the execution would move to whatever locale hosted that variable. It could be an array element, for example, if you've got a distributed array. So that's locality. Here's parallelism. Got a variety of forms, and you'll recall from the X10 talk that a lot of this will look similar, familiar. The syntax is different, but the ideas are similar. So you've got task parallel construct of begin statement. That creates one new task. The new task runs statement. The old task continues on. The two have nothing to do with each other after that. There's no implicit synchronization between the two. You're just creating a parallel piece of work, and it goes off and does whatever it's going to do. There's task parallel constructs. These have implicit barriers at the end. There's a co-begin, which takes a block statement, which is just like in C, a curly brace surrounded sequence of statements. That creates a separate task for each of the statements, and those go off and run. There's also a co-for-all that creates a separate task for each iteration of the loop, and those go off and run. That whole construct then has an implicit barrier sync at the end. So everything will come back together at the end, and then the original task that encountered the co-begin or the co-for-all will continue. That implicit barrier applies only to the immediate tasks created by the construct. If, for example, you did a co-for-all, and one of the iterations did a begin, and thus created a separate, yet another task, that begun task would not be included in the barrier sync. It would be free to continue. So the barrier sync at the end applies only to the tasks that are created directly in the construct. And finally, there's a data parallel style, this for all. This creates some number of tasks, and how many is up to that iteration expression there, the thing after the in. That controls how many tasks there are, how many iterations each one gets, and which ones, and where they run. That iteration, that iterator, will be written in Chapel and will come from a module somewhere, generally, and I'll talk about modules in a second. But this is kind of the workhorse statement for data parallel programming in Chapel. So next, what's the compilation look like? Well, this is gratifyingly simple. So you take some Chapel source code, run it through the compiler, you join it with some standard modules. As I said, I'll talk about those in a second, and you end up with an executable. So what's inside the box? Here's an expansion of that box inside the dashed line. Again, you see the standard modules and the user program, user source code coming in from the left. We compile from Chapel to C. We also get some internal module code written in Chapel inside the box, and I'll talk about the distinction between those internal and standard modules in a second. So you take the generated C code, run it through a standard C compiler, link that up with the runtime library, which is the main thing I'll talk about today, and there's your Chapel executable. So, modules. That's these two boxes here. A module is just an encapsulator in Chapel. It's a way to name a collection of types, variables, and functions, and then use it later in a program. So, users obviously can write modules, and you also get some with the Chapel distribution. There are two different kinds. There are internal and standard modules. The internal ones, these are the ones that were inside the box. If you recall, let's go back. These guys, the internal module is the one on the right, inside the box. Oh, sorry, I left out a detail. To use a module, or to bring the definitions of a module in, you use a statement called use, right? So you say use the module. There's an exception to that, and that's the internal modules. Internal modules are designed to support the language. So the compiler brings those in all by itself. You don't have to use them. These are things like array support, distribution maps for moving array, for laying down arrays on top of the locales, that sort of thing. So no use there needed. Then there are standard modules. These are the ones that come from outside the little compiler box that I showed. This is to support user code. These are things like math, random numbers, timers, that sort of thing. You do have to use those. All right, now the runtime, this box. The runtime's the lowest level of support. It's the bottom of the software stack. Supports the language constructs, provides an interface to system services. It's all written in C. It's composed of what we call layers. That's a misnomer. There's not in all cases a sort of stacking arrangement between these pieces. They're more kind of like posts, right? They work together to support a shared dependent load. The various layers, and I'll show you some examples of those in a minute. The various layers all have standardized interfaces, but interchangeable implementations. That's to support sort of the researchy aspect of Chapel, to allow us to implement various things in different ways and see what works and see what doesn't. You select the implementations of the various layers when you build the runtime using environment variables, and the same environment variables select which already built runtime gets linked with your Chapel program when you compile it. There's the runtime. So those boxes in the middle row are the layers. There's communication, which handles communication between locales. There's tasking, which handles parallelism. There's a memory layer. There are launchers. Launchers basically are the things that start Chapel programs independent of what your system architecture is, because we thought it might be a nice thing if people didn't have to learn all the different, if people could carry Chapel programs from Chapel source code from one system to another and not have to learn how each different kind of system launched multi-locale programs. So we take care of launching for you. We hide that behind the scenes. QIO is a kind of new I/O package that we just added. There are a couple of different implementations of timers, and standard's sort of a catch-all. You can think of standard as all the rest. So let's talk about communication first. Here are the things that the communication layer gets you. We've got put operations as RDMA. Put operations of either single value or multiple values that are strided. Got get operations for single values and strided. That basically you give these things a local and a remote address and a remote locale and data flows whichever way you've specified. In get operations, we've got normal blocking flavor, but we've also got sort of a tentative interface and implementation for non-blocking gets, only for non-strided, just single values, and we're using that to experiment a little bit with lightweight, fine-grained overlap of communication and computation. And we've also got a remote fork operation which runs a function on some other locale. It uses the active message model, which I'm going to assume you're familiar with. Normally on the remote side, the way it works is it starts a Chapel task to do the work. And you have to differentiate here between mechanism and semantics. The task it starts is not a task really in the Chapel sense. It's more a task in the runtime sense, because in the Chapel sense, what you're doing when you do a remote fork is moving the current task's execution. In the mechanism sense, the way we do that is by starting a low-level task, a runtime managed task at the far end and then running that. But it's still at the language level. It's still movement rather than starting it. It's not starting parallel work, not in that sense. So we've got blocking ones. We've got a blocking one. That's the normal. That's what an on statement normally turns into, is a blocking remote fork. That's the local side waits for the remote side to complete and then goes on. No parallelism there. We also support a non-blocking model where the local side, fires the active message request and then just goes on. Mostly that's used internally, but we'll see an example of it here as a result of source code in a minute. And then finally, there's what's called a fast version. If you're familiar with active messages, you know that there are some limitations on what the active message handler can do on the far side of a remote connection. In particular, it can't do anything that might prevent it from being able to handle future active messages that come in as a result of its own activities. And so pretty much in terms of communication, all an active message handler can do is send an ACK back to the originating side saying, I'm done. Okay, what that means is that if you're using this model to fire remote work, you don't want to be just running sort of general code inside the active message handler, because you may deadlock the whole program if that does something that then needs another response back, which requires the active message handler to take care of it. So we can use the fast version here if the compiler can determine that the target function is small, so it won't take long to run, and can't do anything that'll block the active message handler. Let's talk about each of these three instantiations briefly. So we have a Nun instantiation, sort of a proof of concept, right? Implements the interface, doesn't actually do anything, doesn't communicate. But any program, as long as it doesn't really need to run on multiple locales, can run using this one. We use this a lot for testing because it lets you build any old Chapel program and have it work, but you don't have to have multiple system locales or system nodes. Then we have a GASNET COM layer. This is really our workhorse. This is the default in most cases. It's got good performance. It's got great portability. We're using GASNET 1.20, and I went and counted when I was building this slide. They support 16 of what are called conduits. Conduits are GASNET's name for an underlying communication technology. So they build a little thin interface that gives them access to what they need to do in terms of something provided by the system, UDP, MPI, whatever. And there are 16 of them, as I said, in GASNET 1.20, so it's extremely portable. You can always find something that will work on your favorite network system. GASNET is from, I should mention, GASNET's from Berkeley. Started out at UC Berkeley, and it sort of traveled because it was attached to the people who were working on it as they moved to Lawrence Berkeley National Laboratory. So it's sort of hosted out of there now. And then finally, if you're going to sell systems, you probably ought to write software that works on them. So the Cray Networks, the Gemini network that's in Blue Gene over here, and the Aries network, which is the follow-on generation to that, are supported by this thing called Genie, GNI, which originally stood for Gemini Network Interface, and then when we built another chip, changed to Generic Network Interface. Actually, there are two pieces of the interface to that. There's KGenie and UGenie. KGenie is the kernel driver interface. We don't publicize that, not because it's super secret or anything, but we don't want people writing to it because then we can't change it, right? But then there is a UGenie interface, which is public. You can go on the Cray website, go to the support pages of that, and find the manual for this. So we've got a COM layer for Chapel that's based on UGenie. It's got very good performance on Cray hardware. Could be better, but it's still pretty nice. And if you use the pre-built Chapel module on Cray systems, this is what you get. Module here is not the same word as module in the Chapel module sense that I talked about 6 or 8 slides ago. Module here is a shell module, like module use blah. So when we release Chapel, we build a module for Cray systems, and if you use that one on a Cray system, then you get this COM layer. All right, tasking layer. This is actually where I spend most of my time, or at least have in the past. Tasking supports all the parallelism and Chapel programs. So across that first row of small blocks, the Nun, FIFO, MUX, Qthreads, and massive threads, those are the tasking layers. You see that threading thing underneath FIFO and MUX. I want to talk about that briefly in a second. That's kind of a funny story. Tasking layer supports parallelism. It's local to a single locale. There's nothing that would prevent it, but we haven't ever built a tasking layer that would support multiple locales. We leave it to either the user writing, direct on statements, or the author of the iterator for a for all to determine where tasks go. And when you say on somewhere, do this task, it goes there. We won't move it. There's nothing, as I said, to prevent doing that from a language point of view. We just never have. That's not something we wanted to tackle at this point. At this point means any time in the last 7 years. So operations here at the low level to create and start a group of tasks, start a move task. That's basically the operation that I talked about, where you create a task to do the body of an on statement in order that the AM handler not get blocked. There's also synchronization support in here. Chapel has what are called sync and single variables. These are variables that, in addition to normal variable state, also have a full and empty meta state. And when you access them, if you're doing a load and the variable is empty, your task will block until the variable becomes full. if you do a store and the task and the variable is full, your task will block until someone reads it and leaves it empty. Then your store will complete, and then you'll go on. So that's the major way that we provide for synchronizing tasks.
So fair to say that you support continuations in the standard chapter. It doesn't get blocked.
Yes. Yes. Fair to say that general continuations are supported because of the blocking and then continuing. So that threading layer that I pointed out on the diagram, I just threw this in as a confession because this is a runtime talk, and I'm sure none of you who ever wrote runtimes ever did any piece of interface that you wished you hadn't spent the time on. In this case, I wish I hadn't spent the time on this. We thought, actually, that it might be nice to separate the semantic concerns of Chapel tasks from the semantic concerns of the underlying system threads upon which they ran. And when I say system threads, I include third-party, other kinds of threading models beyond just Pthreads or whatever. So, okay, great. So we design an interface. I design an interface. We built a few instantiations of this threading layer. Fortunately, we confined knowledge of the threading layer interface to just the tasking layer and the threading layer instantiations, because, as it turned out, it wasn't really that useful. Didn't turn out to be time well spent. So we, in order to experiment, let's say, do research in terms of with regard to what tasking models work well, we've been fairly active in inviting participation from outside groups to bring, to build tasking layers that would work with Chapel. Well, when they did that, they never wanted to code to our threading layer. They always brought one with them because they were supporting other models as well, and they needed something portable they knew well. So they didn't want to code to our threading layer. So the third-party tasking layers didn't use our threading. And then it turned out to be hard to generalize and still get performance at the threading layer level. The idiosyncrasies of even our own tasking layers were such that they wanted to use the threads in very different ways. And so as it turned out, we weren't able to come up with an interface that really worked well, covered all the needs, and gave good performance. And as a result, as you'll see in the diagrams, even our own tasking layers tend to use specific threading layers, and we don't switch around much. Okay, so if there's ever the time, I'd like to remove this. I don't know if there'll ever be the time. So, like the COM layer, we've got sort of a vacuous, if you will, tasking layer called None. It supports only serial execution. And there I don't mean execution that doesn't involve tasks. I mean execution of a multitask program in which every task that starts finishes without blocking. So, right, if the execution path is such that you can, maybe you could imagine a depth first model with no blocking, where every created task gets run to completion and finish. That'll work fine with this tasking layer. Nothing's ever really parallel, but the program will run. If you ever try to block on, say, a sync variable that's in the wrong state, using the None tasking layer, the whole program will deadlock. But again, this is useful for testing. We use it a lot for that. FIFO, the FIFO tasking layer is our workhorse. Uses a Pthreads threading model. Basically, we tie a Chapel task to a system Pthread for the duration of the Chapel task's life. If a task completes, then the Pthread goes and looks in the pool for something more to do. If the task blocks, we yield the Pthread, and we let the system find another one to run, find another Pthread to run representing some other task. We don't ever give Pthreads up. In practice, if you create monstrously large parallel regions, this can lead to having a lot of Pthreads pounding on the pool of tasks. but it doesn't happen very often. It hasn't turned out to be much of a problem. So again, here, when a task blocks, we switch the thread on the processor. In the Qthreads tasking layer, when a task blocks, we switch the thread on the processor also, but these threads are way more lightweight. Qthreads comes from Sandia National Laboratories. It's a lightweight user-level threading layer. It's got very nice performance. Likely will become our default at some point soon. Not all of our testing passes with Qthreads. We've still got a few hangers on that we need to clean up. But for the most part, this works very well. And it's got much nicer performance than the FIFO tasking layer. But like the FIFO layer, this one also switches threads when a task blocks and ties tasks permanently to threads. The same is true of Massive Threads, which is from University of Tokyo. These are also lightweight threads managed in user space, also tasks tied to the threads for the duration of the task lifespan, switch the threads at task block time. And there was actually, up until 6 months ago, we had a collaboration with Barcelona Supercomputing Center at University of Barcelona using their Nanos package, which was yet again another set of lightweight user threads support and worked the same way as these did. And that one is languishing now. We're not using it actively. Then finally, we've got this what we call the MUXT layer, multiplex tasking layer. This one works a little bit differently. It's still a lightweight thread switcher in user space, but instead of switching threads, instead of tying tasks permanently to threads and then switching threads when the task block, it lets the tasks multiplex on the threads, and it switches tasks on the threads when the task block. This one's got very good performance, and is the default along with that Eugenie COM layer when we're using the pre-built Chapel module on Cray systems. Okay, so that is all the tasking layers. And just a word about the memory layers. There are 3 implementations here. There's a default one built on top of the usual Linux malloc free ... There's DL malloc. I'm not sure how many software packages there are in the world that are actually named after their developer, but there's DL malloc. We use that with GASNET, with the GASNET COM layer, and I think that may have been at their recommendation. It facilitates sort of high-performance mode of GASNET, where it knows, where it has a better idea of where all the data is located, and so it can do simpler memory registration. And then finally, there's a package called tcmalloc from Google Perf Tools. This one is actually the one that we use with the Eugenie COM layer. Similar to the DL malloc package, allows us to, in particular, to use huge pages, which simplifies memory registration for the Genie hardware, for the Gemini and Aries hardware. Partly that's due to the fact that the TLB on the Gemini hardware and the Aries hardware is a little bit limited. It's only got 16K entries, and so 4K pages are just not big enough. So you don't want the memory to be lying all over the place. You really need to kind of gather the memory into a block of huge pages, register that, then that works well. So those are memory layers. Let's run through an example. So I stole this from HPC, the HPCC remote access benchmark, HPC challenge. What we've got here is we're going to do atomic exclusive OR updates to an array of atomic, in this case, LM type turns out to be a 64-bit integer. And that table space is a distributed domain, what's called a domain in Chapel, which basically means that it's a range of index values along with a description of how those are mapped onto the locales that the program's running on. Could be blocked, could be single. Doesn't matter. So we do a for all over that iterator expression, which is a zipper. So updates, the first argument there, is a distributed domain. It's not the same one as table space. This is a distributed domain of the iterations of the loop, that is the updates to the array, and where those should run. So think of it as just a range of values, and again, a description of where those values lie on the locale space. Then our A stream is just a stream of random numbers. The zippered iteration, the zip operator, combines those two pairwise, forms a tuple for each iteration, and then you'll notice that underbar inside the tuple in the parens in the parentheses after the for all. We throw the iteration number on the floor because we really only wanted it to tell us where to run and how many iterations the loop should have and how many iterations each task should get. So now we just throw it away because we don't need it, and we use the random number part of it in the body of the loop, which does an exclusive OR, an atomic exclusive OR, on each element of the array. Okay? So there's our loop. Question so far? All right, good. The loop turns into, effectively, the stuff in the second box. So I should say, before we get too far into this, that none of this is exactly how things will work. Partly that's because that iterator up there, especially the updates part of it in the top row, that's potentially user-written. You can write your own domains, distributed domains, and the iterators attached thereto, which will describe how iterations, how elements of a range get distributed over locales in a running program. So I don't know exactly how the iterations of updates will get distributed, but what I'm going to show you is certainly a reasonable approximation. It's one that could happen. And if you're using the right distribution that comes with the internal modules, it's the one you'll get. Okay? Yeah? Yes. Yeah, there are restrictions on, so this is, we use what are called leader-follower iterators. The thing on the left, the updates, is called the leader iterator. It actually determines how many iterations there are and where they'll run. The other if there are further iterators or further elements in the iterator, those are called followers. They just follow along in terms of location. Any location information they give is simply ignored. They have to be restartable at any point. You have to be able to run them from any point in their sequence and get the same value that they would have given had you run the whole mess in serial. So, yeah. So effectively what this turns into is a co-for-all. Remember the co-for-all creates a task for every locale, and co-for-all creates a task for every iteration. In this case, we'll run each iteration on a separate locale, and then inside there we'll do a single locale version of the for-all that, again, creates some tasks and splits iterations out among them. So we're dividing the work in two ways. First across the locales, and then within the locales. You can assume in general that the number of updates here, that is the total iteration count, is way bigger than the number of locales. Because if you look at how much work there is in that body, it's not much, right? You've got a load, a store, some arithmetic to do the indexing and the exclusive OR, and that's it. Which means that you're going to need a fair number of iterations of the loop in order to amortize the costs of making tasks and doing remote on statements to divide the work across the locales. All right. So what's that first co-for-all look like? So the corresponding runtime calls. This is actually a really common code idiom, so we don't do things the way the way I described earlier for the for the co-for-all and the on. We don't actually create local tasks for each of the iterations of the co-for-all and have them do a separate on. We run into that line of code so commonly that actually what we do is run through a loop on the originating side, run through a loop that does a non-blocking remote fork to fire a task body containing the body of the co-for-all on all of the locales that are not us. And then after having done so those are all running, and that's a non-blocking remote fork, so it just fires it and on we go on our side. And then on the originating side, we just call the task body or the on body directly. So that's the originating locale side. On the target locale side, so the reason that's in bold, that ChapelCom fork NB, I shouldn't be pointing at this screen. I should be pointing at this screen. The ChapelCom fork NB is in bold because that's an actual runtime call. Then on the target locale side, the active message handler here gets the request and does a Chapel task start move task with that compiler built task body, and that will do the body of the co-for-all on the remote side. So we've done the distribution of the iterations of the outer loop across all the locales. The middle loop is conceptually actually rather easier. So that's single locale, so there's no communication. There's just a sequence of calls to the tasking layer of the runtime to create the descriptors for the tasks, launch them, ensure they've started, and then finally clean up after the barrier for the co-for-all the barrier for the co-for-all part of it that makes sure that everything is done. This piece of the interface could be simplified. It's sort of inherited from the first implementation, and we never did really go back and simplify it. In particular, in some implementations that execute tests in list functions actually empty. So now we've got all the tasks running on the local locale, and all we got to do is run the body. So that's that exclusive OR. Compiler has to go find a definition of the exclusive OR method somewhere in the internal modules for atomic data, and it turns out there are more than one. There are two cases. There's one where the network doesn't support network atomic operations, and there's one where the network does support them. So without network atomics, we have to run sort of generic code that'll work anywhere, right? And in modules internal atomics.chapel, there is a method definition for that exclusive OR that basically says on this do an atomic fetch and XOR. And what that does is move execution to the far side, use a processor atomic to do the operation. So although that's a little expensive because you're going a long way across the machine to do a few integer instructions, but it works, right? And sometimes anything that works is better than anything that doesn't. So this is sort of the default case. And what the code turns into, the body of that little method, is a ChapelCom fork off to the locale that owns the element of the array in this case. The active message handler starts a task over there, and that does the atomic fetch the atomic fetch and exclusive OR, and then sends back an acknowledgement. And that lets the ChapelCom fork continue. So that's the blocking aspect of it. Now, in practice, this actually might turn into a fast fork. I've sort of hidden the detail here. Active messages allows in fact, it requires the active message handler on the remote side to send the ACK, right? So that doesn't count as something that could block things. That ACK has to be sendable. So in practice, what would happen here is there would really be two wrappers. There'd be a task wrapper that sent back the ACK, And then there'd be another wrapper for the user code. That's the part that's not allowed to do anything that might block stuff. And so the compiler would look at that and it'd see that that processor atomic operation there and say, well, that can't block. And so this might well turn into a fast fork. A fast fork would be handled directly in the active message handler. And the benefit of that is twofold. One is that you avoid a bunch of calls. The other is that obviously you avoid queuing a task to do the work. That has a fair amount of potential overhead depending on how busy that far side is. Okay, so that's the case of no network atomics. If you have network atomics, and the Gemini network, as on BlueJean, can do atomic operations directly in the network. Integer ones on Gemini and the Aries follow-on, you can actually do a floating point add atomic in the network if you want, and a variety of other floating point stuff. So if the network supports that, and you're using a COM layer, it supports it as well, then we pick up a module to satisfy that XOR method from a different place. This one comes out of the specific Eugenie COM layer internal module. And that method just does a COM layer call to do the remote atomic operation directly. And then we're done. So that's the example from Chapel source code all the way kind of to the depths of the runtime. Where are we headed next? The biggie for this year is hierarchical locales. This is to support hierarchical, heterogeneous stuff, GPUs attached to CPUs, as on some of the nodes of BlueJean. We're starting to sell a lot more systems that have at least partial population with GPU blades instead of just CPU blades. So this is going to be a big deal for Cray. And there are many core CPUs coming. We have for some time wanted to take better advantage of NUMA domains even on pure x86 nodes. So we're headed that way now. It'll affect a little bit the memory management. In particular, if you're allocating memory on a GPU-equipped blade, you have to know whether you're getting GPU memory or CPU memory. Probably have a bigger impact on task placement because there's not only the GPU question there, but even on a NUMA x86 domain, you'd like to put tasks on the right piece of the NUMA architecture of the target locale. So currently, the compiler emitted code that I was just showing emits that stuff calls directly to the runtime. We're going to put a middleman in there. There will be an architectural description, a new internal module. Actually, yeah, I think it'll be an internal module, but we'll probably allow people to override it. We'll probably allow people to write their own standard module for some peculiar architecture that they're interested in. And the compiler emitted calls will go to there, and that will decide how to distribute them, whether a given memory allocation request should go to the GPU side or the CPU side of a heterogeneous node. We're hopeful that in terms of the impact on performance, at least for the current set of architectures we support, that we can sort of collapse that call chain so that there's not really any, in the end, there's no module code interspersed. What else? For some time, we have wanted to work on task teams for collectives, that sort of thing. On Eurekas for short-circuiting searches. And on task private data, which is a supporting capability for both of those. Obviously, you can build task private data now if you create a task and put the data on the stack and then include it in your call chain all the way up, but that's kind of a pain. It would be nice to be able to declare something, say, at the module level as task private, and then every time you made it a new task, it would inherit its own copy of that. So that's something we'll want to work on. And with that, questions?
or two short questions? Otherwise, we should discuss them and take a break. Any questions?
I either confused everybody
Or everyone understood.
covered it perfectly.
So I question at the tip of my tongue, but I've lost it now. So okay, that's actually a very narrow question, but since I have the random stream that you talked about, and you said ith member will get the ith thing, but your transformation kind of seemed to have lost that correspondence.
Yeah, I did. It was a problem how much detail to put in that would obscure really what I was trying to cover and how much to leave out. Yeah, that is, the way that works is mediated by the fact that RA stream iterator is a follower and has the capability to give you, you tell it I, and it'll give you the I thing that it would have produced. Right. So every time you fire when you fire the on body out of the top coverall, maybe I should go back to. Right. So this top box, when you fire the on body for the top box, actually it's one back. Right. You'll include the range of eyes that RA stream needed to. And then when you fire the task body for the middle loop, you'll send that task body its range of eyes, and then it'll tell RA stream, okay, give me that block of. So that's how that'll work.
Thank you. Well, that's